Thanks and hi everyone. My name is Peco Elenchevski. I am from the Deutsche Bahn AG, and me and Nico Becker from the Thamm GmbH are going to talk about an interesting use case we have here at the Deutsche Bahn, how we developed the proof of concept for it and how we are planning to bring this use case into a productive system. So first things first, here's a quick overview about the topics we are going to talk about. In the first half of the presentation, I will talk about the use case itself and how the technical background looks like. And in the second half, Nico will take over and he will talk about the machine learning operations and how to bring this use case into a productive system. But before we dive in, we each want to introduce our teams real quick. I am an AI engineer for vsion.ai, which is a venture founded by DB Systel, which itself is a subsidiary of the Deutsche Bahn AG. We are a growing team of 13 people, including interns and 3 interns and students. And our main focus is applying computer vision to and machine learning on visual data that is relevant in the context of Deutsche Bahn. At the moment, we are especially invested in maintenance and the health of the infrastructure. Our goal is to use state-of-the-art technology to ensure a better experience for our customers. For example, with better checks on the infrastructure, we can ensure fewer delays. With efficient maintenance programs, we can further secure the safety of our travelers. And all of those goals are brought forward with the help of new technologies, including deep learning.
Hello, also from my side. My name is Nico Becker. I'm data scientist at the Thamm GmbH, which is the #1 company for data and AI expertise in Germany. Ever since AT was founded, our mission was to bring our clients forward by helping them implement data and AI solutions. We right now have more than 200 employees. We also have an internal training program and already apprenticed more than 50 data trainees. And across all industries and clients, we already implemented successfully more than 1,000 data and AI projects. And we are happy to collaborate with DB and vsion.ai.
Right, so it seems kind of natural for us to join forces. We are a small team with deep knowledge of railway processes, and Thamm, the people at Thamm, on the other hand, are experienced in different industry sectors. And they can also help us bring our solutions to a higher level by being able to scale up our solutions. And both of our teams are experts in the field of computer vision and machine learning. And our agile mindset is, we think, key to solving most of the hard-to-tackle problems in a flexible manner. Okay, let's talk about the use case. In maintenance, we are often faced with problems that can be tackled by visual inspection, by looking at the problem. For example, we can answer questions like, is there a loose cable somewhere? Or are there screws missing? Are components broken? Things like that. Furthermore, we can also identify trains by looking at the letters and numbers that are written on the trains itself. And identify the wagon number, for example. And fortunately, we can automate most of these tasks with machine learning. For this talk, we are going to focus on the detection of graffiti on the trains, since most of us who travel by train are already familiar with this problem in one way or another. So what are the pain points with graffiti? First of all, it disturbs the comfort of the customer. They miss out on the experience by not being able to look out of the window. But more importantly, though, graffiti might obscure important information on the train for groups of people that might need assistance, such as elderly people or people with disabilities, people in a wheelchair, for example, or pregnant women. And they are dependent to know which door they can use so that they can actually ride the train. And also people tend to feel more safe in an environment that is taken care of more regularly. So we have a big incentive to clean the trains fast. From the operational side, it takes some effort to even detect the graffiti. Every time a train driver takes over a train, they need to manually inspect the train. and report their findings to the respective instances. Those instances then schedule the cleanup, and they schedule this cleanup based on different factors such as train availability or minimizing cost. And the cost is a lower 8-figure amount annually, somewhere like that. Lastly, you need to be able to document when a graffiti was first spotted and when it got removed to ensure transparency. All of these things we try to address with our solutions, and we hope to reduce the amount of manual work done in this field. And we hope to do that in order to cut costs and by helping to make the whole process more faster. Our customers can then enjoy clean trains more often. All right. Now let's have a look about how one could solve the problem by spotting the graffiti not manually, but rather with the use of machine learning algorithms. So what we use is a so-called semantic segmentation with the help of a convolutional neural network, or CNN in short. On the left side here, we have images of graffitis. In this case, we took them ourselves. We had like 100 or 200 images that we used. We then go in with a annotation software. We label the images, so we sit there and really trace the graffiti out, and you can see that on those images with the green splashes in front of the black backgrounds, and those are the masks. And we then take these masks and together with the images and feed them into a CNN, and the CNN then starts to learn about the specifics of the images, and with the masks we can tell them where there's actually a graffiti. After each iteration of the training, there are more iterations than one. After each iteration, there is an error calculated, and this error is then used to adjust the weights that are set in the convolutional neural network. And by that, we can do more iterations, and after every iteration, the model tends to get better and better. And after we have a model done, finished, we can do predictions on images, and those predictions also give us masks. These are those blue masks that are on the right side, and we can then take these predicted masks and can compare them with our annotations, and we then can measure a difference between those two. And this can help us evaluate our model. So when we think that our model is efficient enough, we can take it and use it in application. And this is now where the interesting part starts, because oftentimes you get a model, but you cannot really use it because you also need lots of applications around the model that you can use. So for example, you want to insert new images into the model, and you want to detect how big the graffiti is in relation to the train. So you need different tools for the people. So you will need, for example, a front end where you can put the image, and then in the background it applies this image onto the model, stuff like that. So there are lots of other things that we need besides a model, and we will talk about this later in more detail. And for this proof of concept, we also utilized transfer learning by using ImageNet. And that means we don't train a model from scratch, but we rather use an existing model that has already trained on millions of images. And we just add our graffiti images on top of that. We use that because oftentimes it is, first of all, every time it is better to use more images than less images. But in this case, we also, those 14 million images were also from different classes. So everything you can think of, dogs, cats, and tables and everything. And usually a model tends to work better if you teach it to distinguish between different things. So we use that in order to get a good performance. Now here we have a quick demo. We can see here are the little boxes that show that graffiti were detected, and right, so graffiti was detected with a confidence of 100%. You can see that with the boxes, and in there it says 1.0. That is good. And on the right side, you can see that on the billboard, there was also 2 graffitis detected. This is interesting because this is obviously not a graffiti. You can see that there it says tag 97% and graffiti 78%. And the tag is those little smearings that look like signatures. We distinguish between graffitis and tags. And with this confidence, you can apply a threshold. So you could say, just show me graffitis where you are confident with more than 97% of the time, or with a confidence of greater than 97%. Right, now just a few words on what we think are crucial success factors. First, having lots of data is key to a good machine learning model. Even data that is not directly related to your problem can be beneficial, as seen with transfer learning. Second, the quality of the annotations is oftentimes neglected, but in reality, a slight change in annotation quality can make or break your project. So you should never hesitate to bring specialists for the use case on board. So if you're trying to annotate specific components, you might let the colleagues annotate the images that actually work with these components, because they know them from every angle and for every lighting condition. And lastly, we believe that working in an agile environment with a close focus on customers' needs is important to be able to react quickly on changing demands. Now, set aside the work ethics of the team for a minute. What else do we need except a model that detects graffiti in order to be successful? We need lots of storage space that is reliable to store the data you want to train on. We also need a good labeling tool that lets us work fast and precise at the same time, because this is a huge cost factor. Every second you can save on one image, because you will annotate probably hundreds of thousands of images. This will accumulate pretty fast. And you also need a way to monitor and document your experiments, since you might execute them multiple times with different parameters. But you can have many more applications also, but it's not sufficient enough to just use and have those applications. You also want them to work in synergy, and that way you can automate the process more reliable. In other words, you want your work to be less like that of a carpenter that crafts unique items for every customer, and be more like that of a modern factory that utilizes its infrastructure to suit lots of different customers, and customers that might even present themselves in the future. And with that being said, I'll hand over to Nico, who will go into detail on how you could go from working like a carpenter to building a modern production line.
So yeah, thank you, Peco, for presenting this very exciting computer vision use case. I would now like to pick up at this point and recap the situation. So the idea is we started from a business case of optimizing graffiti removal in Deutsche Bahn context. And what we now have is we have a model which is capable of detecting the graffiti. But what is missing now? As Peco already outlined it, next step would be putting this model into production. I mean, that's said very simply, right? Just put something into production. But I think that this is easier said than done. So let's first have a look at what a worst case scenario of simply putting something into production might look like. So on the very left-hand side, we have this highly simplifying visualization of an ML development process. So starting from a business case, data scientist teams start and they implement a solution with data pre-processing, and then they write an algorithm for training the model. Then they train the model, evaluate if the model is already good enough, and then they make changes on the code, they retrain again, they evaluate again, until finally the perfect model pops out. And so now we have the perfect model. So the data scientists are ready with their work, right? That was their task. They had this business case, they solved it, they have the perfect model. Now they put it into production. So what this means is they take their model and give it to the operations guys. And you can imagine the faces of the operations guys now. Now they hold in their hands this perfect model, but where to go from here? They haven't been involved probably in the implementation of this process. They don't know how they should pre-process data, how to query this model. Probably they might even don't understand the language the model was, the code for the model training was written in. So the challenge now is really putting this model as it is into production, like serving it from some point, adding business logic around it, and make sure that it delivers the same results as it did during training. And if there's no collaboration between data scientists and operations, this might turn out a very hard thing to do. For example, they could even end up taking the parameters of a model trained, for example, in Python, and then have some regression function, and they take these parameters simply and write it in another language and just paste the parameters there. So this process would then be very error prone, and you're not really sure that in the end you get the same results in operations as you did during training. And what then is also missing, you get new data during a production scenario, right? So you have data you have never seen before, and you don't know how your model will operate on these new data. So it might fail totally. And so you need to add a feedback loop somehow. But if those two parts, the data science part and the operations parts, if they don't talk to each other, then this will very likely fail. So the question is now, how can we solve this problem? And for this, I would just like to take a step back and see what's required in order to do a successful operation of machine learning solutions. So here we can see what's all part of a successful machine learning solution. And we see the actual model development is just a small red point right in the center of it. And around that, we have a whole landscape of different tools or requirements that we need to add to this in order to operate those solutions successfully. So for example, in the end, training models is still writing code, right? And we want code which runs in production. We want it to be tested. We want to be able to automatically create new models. And if we have many models, we want to be able to manage those models and also version it. And we have our training data and we have live data, but training data, this is also split into training and validation and test data sets. So we want to exactly know which data we used for which part of the training. Of course, this data needs to be labeled and this all needs to be managed. Then we have something which is called data intake, which is a definition of how the data comes into our system. So what pre-processing steps need to be taken here, from what API is it called, or where does it come from? And of course, if we deploy something and we want to make it very successful, so it gets more requests and then becomes more requests, we also want to be able to scale the solution that we can serve this increased amount of requests. And last but not least, we want also to be able to monitor our deployed solution so that we can decide on retraining the model, or if we can simply be happy that it all works fine as expected. And yeah, in order to address this challenge or to have a look at this whole picture of this world, an approach has evolved which is called machine learning operations. And on the next slide, we will have a look at what this actually means. And the idea is that we take this highly experimental and iterative process of machine learning and somehow marry it with well-established DevOps practices. But it's, again, not as easy as it sounds. So DevOps practices primarily originate from software development. And what makes machine learning different from classic software development is that it's even more experimental and even more iterative, and that already during training and development, we need a huge amount of computing resources, right? We have a lot of data, probably images or audio files or something like this. And then we need GPU power in order to train our models and to make our experiments. And we have lots of data, we have lots of trained models and metadata we log. So we have to really manage a huge amount of stuff, and we have a high requirement for computing resources. So first thing MLOps wants to address is that we provide data science teams or machine learning teams a platform which fulfills all those requirements and serves this iterative process. And once we are able to accomplish all this and train our nice models, we also want to be able to serve them and then to monitor them and to retrain them. And this is where these DevOps practices come in. So this is then about automation and productionizing and quality checking. But machine learning operations is not only a process. It's also about people, and it's also about tools. So in this very first example I showed you, where the data scientist throws the model over the wall to operations, we have two very different roles. Here in the people stream, you can see the data scientist on the very left and the ops engineer on the very right. So very extreme positions here, and they haven't talked to each other. They were basically separated and had no shared knowledge. And this makes it pretty hard to successfully deploy a model in an operative scenario. So the idea of MLOps is that we have a MLOps team working on the project, and we have different roles, not only data scientists and ops, but we have here named ML engineer, data engineer, and a software engineer. And the important thing is that those roles are all overlapping. So, for example, if you take the ML engineer, you can see this role as the glue between all the other roles and the glue between the ML world and the DevOps world. And this makes sure that everybody in the project knows what to do and that no details are getting lost. And they don't work sequentially together, but they work in parallel on the same project, like DevOps teams also do. And then also we have tools, and of course machine learning have their very specific sets of tools. Just to name, for example, TensorFlow as a machine learning environment, and then we want to orchestrate workflows and write machine learning pipelines and reusable code. So there are also some solutions for this. And on the other hand, on the operations side, we have what is called a GitOps ecosystem. So this is all about building CI/CD pipelines and automations around Git repositories. So now that we have kind of defined MLOps and what this is all about, I want to take you back to the Graffiti use case and talk about how we can apply this MLOps approach to the Graffiti use case. So we have a very simple image here, and we start on the very left, where we see this box which says model development. And this represents this experimental and highly iterative process of developing machine learning models. And we want to keep it this way because it's natural to develop machine learning models in this highly iterative way, because we try and fail fast and fix things and then try again. But the key is that what pops out of this model development is just code. And this code we don't want to hide somewhere on a local machine, but we immediately want to have it versionized and in some source control repository. Because as soon as we have this code in the repository, all changes made to the code are visible. And as soon as we have this in some public place, we can start building automation around this code. So we can start building automated retraining pipelines of this model because we have the model code. So we can set up this retraining pipeline. In addition to this, we can also apply software tests to this code and make sure that its quality is good enough for our purposes. And so in the middle box, what we already had achieved is that we have a pipeline which can generate at any time a model based on the same training data as we used during model development. And if we then have this trained model, we can also put this into production. And this is very much easier as in this original example where some data scientists gave some model to some operations guy, because here we have the code that generates the model. We know exactly how the model looks like, and we know that it will always look like this. And so we can automate this. And then we can achieve something that provides the data scientist teams really with a big red button which says deploy this model, because at the moment he checks in a new version of his model code, then all those automated pipelines will run, and in the end, if the new code fulfills the quality criteria, we have a new model in production. And the last point in the top and the bottom right corner is performance monitoring, and this is also very crucial in this entire setup, because as I already mentioned earlier, images or data we see in production might look different than those we used during training. For example, trains could have different colors, graffiti could have different colors, or the styles of the artists may be different. So it's very important to monitor the model performance and see if it still fulfills our requirements. And if it does not, then we can say we just run the model retraining pipeline with some new unseen data. Or if it diverges totally, we can also say, okay, we have to go back to model development. So in summary, we now took this experimental approach and left it as it was, but embedded it in a highly automated environment. And yeah, with this, let's go back to Peco for a quick summary of our session.
All right, thanks, Nico. Let's wrap it up real quick. We saw that the process of removing graffiti on trains can be optimized by machine learning, but that just having a nice model to detect graffiti is not enough. We cannot just throw it over the wall to our colleagues from operations and hope for the best. We rather need a whole ecosystem of solutions to work in synergy in order to build a robust and resilient solution.
Okay, so thanks for this quick summary, and thank you guys for your attention. I hope you liked the talk, and if you have any questions, we will stick around, or one of us will stick around and the other one will be in the chat. So don't hesitate to ask your questions. We are waiting for them, and yeah, feel free to get in contact with us. So here you have again our contact data. And Alexander Thamm GmbH also has a virtual booth at Data Festival, so make sure you step by. Yeah, enjoy the rest of the show. Thank you.
Thanks.